Hi, in this video, we're going to talk about what are called independent random variables, and this shows up often, not only in for this exam, on future exams, and even in your everyday work as actuaries. Independent random variables are show up very often. So let me introduce this with an example. So let's say that we have this joint distribution table for random variables x and y, cap x and cap y. So we talked about how to read the values in the table before. For instance, the 0.15 would be the probability that cap x is equal to 2 and cap y is equal to 1. And likewise for the other values in the table. We talked about getting marginal distributions in the previous video, so we could get, for instance, what's the probability that cap x equals 1, the marginal probability that cap x equals 1. I need to look at, I add up the row where cap x equals 1 and I get 0.35, so that would be the marginal probability that cap x equals 1. Likewise, the marginal probabilities for cap x equal 2 and 3 are 0.25 and 0.4. And then I can look at marginal probabilities for cap y. Cap y could be either a 1 with a probability in the margin there of 0.6 or a 2 with a probability of 0.4. Notice that all the values are, the sum of the rows are the columns, and the probabilities that I'm going to use for the marginal distribution for x add up to 1. The probabilities that I'm going to use for the marginal distribution for y, the 0.6 and the 0.4, add up to 1. So everything's good here. Everything's consistent. And so I can actually just list out the marginal distributions for cap x and cap y. Again, cap x could be a 1, 2, or 3 with probabilities 0.35, 0.25, and 0.4. And cap y could be either a 1 or a 2 with probabilities 0.6 or 0.4. And I could even do some conditional probabilities which give rise to the conditional distributions. So for instance, let me make one up. Let's look at a conditional distribution of cap x given that cap y equals 1. I just made up, or just picked one. Cap y equals 1. So now what are these probabilities then? What are the conditional probabilities that are going to give me the values that define the conditional distribution? So the probability here, and where the question mark is, I'm actually asking then what's the probability that cap x equals 1 given that cap y equals 1? And I know that that's the ratio of the, so this is a conditional probability. It's going to be the joint divided by marginal. So I'll look at the joint probability where both cap x and cap y are 1. That's 0.21. Divide that by the marginal for cap y being equal to 1. The marginal for cap y at 1 is 0.6. And that ratio there, when you take that ratio, you get a 0.35. Likewise, if I want to move on to the next value in the table, I'm actually seeking the value of the probability that cap x equals 2, given that cap x equals 1, which I know that to be the joint probability that cap x equals 2 and cap y equals 1, divided by the marginal probability that cap y equals 1. And so that's going to be, when I pluck out the values in the table, the 0.15 in the numerator and 0.6 in the denominator, and that ratio is a 0.25. And then finally, for the third value in the table, if I want to go through this process the same way that I have before, that I'll just calculate the conditional probability that cap x equals 3, given that cap y equals 1, and pluck out the corresponding values in the table, the 0.24 over the 0.6, and that value is a 0.4. Now notice if I had the first two probabilities, the 0.35 and the 0.25, I didn't really need to go through the process that I have shown right now to get the last value. I could have just taken a 1 minus the sum of the previous two, or 1 minus the 0.35 minus 2.25, and you'll see that that's actually a 0.4. What I really want you to notice in this, though, is that look, I get the same distribution as the marginal distribution for cap x. I got the same, cap x, the values could be either a 1 or 2 or a 3, and the probabilities are exactly the same. The corresponding probabilities that are defining the distribution are exactly the same, 0.35, 0.25, and 0.4 respectively. So the conditional distribution of cap x given cap y is equal to the marginal distribution for cap x. And likewise, if instead of conditioning on cap y being equal to 1, watch in the next slide, I'm just going to put a slight little subtle move there where cap y equals 1, now cap y equals 2. I'm going to leave it to you to show that you'd get the exact same values there. The 0.35, the 0.25, and the 0.4. I'll leave it to you to show that. So again, I get the conditional distribution is actually equal to the marginal distribution. In other words, what this is telling me is that the cap x, the probabilities that cap x is equal to a 1 or 2 or a 3, it doesn't depend on whether cap y is equal to a 1 or whether cap y is equal to 2. It's independent of cap y. Okay, I'll come back to that statement in just a second. Okay, so the conditional distribution of cap x, given that cap y equals 1 or a 2, is the what I mean by this is it doesn't matter whether cap y is equal to a 1 or whether cap y is equal to a 2. The conditional distribution of cap x based on that event would be the marginal distribution. I invite you to see that the same is going to be true for cap y. If I condition cap y on the event that cap x equals 1, or on the event that cap x equals 2, or on the event that cap x equals 3, I get the exact same thing as the marginal distribution of cap y. And this is what is meant by when I say that the random variables cap x and cap y are independent. They don't depend on one another. The value of the probabilities that I get for, that cap x is equal to a 1, 2, or 3, they're independent of cap y. They don't depend on what cap y is equal to. That's independent. So the random variables, I would say in this case that the random variables are independent. Okay, so now let me go back to the table first, the table that was given with the marginal probabilities that are in there. And let me just show you a quick, easy way to see whether you've got independent random variables or not. Notice that from the marginal distributions, I'll highlight in red the marginal distribution 0.6 for cap y being 1 and 0.35 for cap x being equal to 1. When you multiply the reds together, 0.6 times 0.35, you get 0.21. And if you'll do this for all the different combinations and permutations and so forth, 0.6 times 0.25 would be 0.15. It is 0.15. 0.6 times 0.4 is 0.24. 0.4 times 0.35 is 0.14. 0.4 times 0.25 is 0.1. 0.4 times 0.4 is 0.16. That's what's going to give me, that's how I know I have independent random variables, just by looking at the table. I fill in the marginal probabilities and then I multiply see that when I multiply marginal probabilities, whether or not I get the joint probabilities, and if I do, then I have independent events. Okay, I want to make another couple of comments here. So let me just pick out a couple of, one specific case. So the 0.15 is equal to the 0.6 and the 0.25. The 0.25 and the 0.6, I've color-coded these for a reason. So where do these probabilities come from with respect to what events are they the probability of? The 0.15 is the probability of the event that cap x is equal to a 2 and cap y is equal to a 1. The 0.25 is the marginal probability that cap x is equal to 2, and the 0.6 is the marginal probability that cap y is equal to 1. So that's where they came from. So let me clean up the slide. It's getting kind of too crazy there. I want to focus on now the left-hand side there of that last equation. I have the probability. I have something that looks like the probability of an A and B, where A is the event that cap x equals 2 and B is the event that cap y equals 1. So what we're doing here is we're applying a lot of the things that we learned in the first module just to specific events that involve random variables, events that are defined by random variables. So on the left-hand side, I've got the probability of cap A intersect cap B, and I know that that's always equal to the probability of cap A times a conditional probability that cap B is cap B given cap A. So let me focus on that last factor, the probability that probability of cap B given cap A, and fill in the events that cap B is the event that cap y equals 1 and cap A is the event that cap x equals 2. But I found before that this conditional event probability that cap y equals 1 given that cap x equals 2 x and y are independent, and so the probability that cap y equals 1 will not depend at all. It's independent of what cap x is, so this is just equal to the probability that cap y equals 1, which is the probability of B here, the event B, what I defined as the event B. And so in this case, I have the probability that cap A intersect B is equal to the probability of cap A times the probability of cap B. I'm just tying it back to some stuff from the first module. In other words, from the first module, we would know that these events then are independent events. So I've talked about independent random variables, and all I wanted to show you through the last few slides is that when we talk about independent random variables, we're being consistent with what we've done before where we had independent events in the first module. So independent random variables, the terminology is consistent with independent events. So okay, finally, one other thing with respect to notation. So let me clean the slide up again. I've talked about this notation before. On the left-hand side, that probability is actually a joint density function for cap x and cap y evaluated at 2, 1. Cap x is 2 and cap y is 1. And on the right-hand side of the next to last equation, where I have the probability that cap x equals 2 times the probability that cap y equals 1, using density function notation, that's the marginal density of cap x evaluated at 2 times the marginal density of cap y evaluated at 1. And so generally what's going to happen is that if you have independent random variables, your joint density function is just going to be the product of the corresponding marginal density functions. So the joint density function will be the product of the marginal density function. So let me summarize it. Let me summarize one last slide here, or two last slides. And when you have for all events A and B, so in the top left, going back to this, what's on the top line here, the top row there of this slide is information from Module 1. And let's apply that information from Module 1 to what we've just learned with multivariate random variable context, and in particular independent random variables. So on the top left in red, for all events, when you take a probability of an A and B, it's the probability of A times the conditional probability of B given A. And for all random variables below that, for all random variables, the joint density function is the product of the marginal density function times the conditional density function. So I hope you can see the analogy there. But then if you have independence, if you have independent events, the probability of event A and event B is just the product of the probabilities of events A and B. And so the conditional part falls out because of the independence. And likewise, if you have independent random variables, the joint density function is just going to be a product of the corresponding marginal density functions. Okay, so we're going to be using the independent random variable stuff is going to show up all throughout the rest of the course, and also pretty much throughout the rest of your career if you become an actuary. Okay, I'll see you in the next video.